Inspired by Breakthrough Starshot, an ambitious project unveiled in 2016 by Breakthrough Initiatives, humanity sets its sights on becoming an interstellar species. The concept was revolutionary. To craft a minuscule spacecraft propelled by a light sail, capable of hurtling through space at speeds which could see it reach Alpha Centauri, our nearest star system, within 2 decades. The key to this extraordinary journey lays in the development of cutting-edge technologies. Central to the plan was an intricate array of millions of lasers, meticulously synchronized to track and propel the light sail across the vast cosmic expanse at speeds approaching 1/5 the velocity of light. In December 2021, the University of Sydney and the Australian National University provided updates on their contributions to the Breakthrough Starshot project, signaling ongoing efforts to advance the necessary technology. In 2015, Israeli billionaires Yuri and Julia Milner established Breakthrough Initiatives, driven by the profound quest to search for extraterrestrial intelligence. This ambitious endeavor is delineated into various key projects, each poised to tackle different facets of the cosmic enigma. Among these ventures, Breakthrough Listen endeavors to scrutinize 1 million stars for any trace of artificial radio or laser signals, while Breakthrough Message aspires to broadcast a communication into the depths of interstellar space. However, the crown jewel of Breakthrough Initiatives is undeniably Breakthrough Starshot. Originally reported by Newsweek in 2016 as a collaboration between Mark Zuckerberg, Yuri Milner, and the late Stephen Hawking, this venture received a substantial infusion of $100 million. It's a lofty goal: to revolutionize space travel by developing a proof-of-concept technology capable of dramatically reducing the time required to reach our nearest stellar neighbor, Alpha Centauri, to a mere 20 years, a prospect tantalizingly within the grasp of our lifetimes. The magnitude of this endeavor is best grasped when considering the staggering distances involved. Alpha Centauri lies a mind-blowing 40 trillion kilometers away from Earth, necessitating a breakthrough in propulsion technology. To put it into perspective, contemporary spacecrafts employing ion thrusters, the pinnacle of current long-duration space travel technology, would require a daunting 18,000 years, or approximately 2,700 human generations to undertake the journey, as estimated by NASA. Mark Zuckerberg succinctly captured the significance of Breakthrough Starshot in a 2016 Facebook post, highlighting the tantalizing possibility that habitable planets may orbit stars within our cosmic neighborhood. The prospect of potentially photographing such planets, particularly those orbiting Alpha Centauri, fuels the project's importance in the quest for extraterrestrial life and our understanding of the cosmos. Central to the success of Breakthrough Starshot is the development of an ultra-lightweight spacecraft dubbed Starship. Multiple teams have been tirelessly collaborating to refine various aspects of the technology. Professor Martin Desterke's team at the University of Sydney, for instance, focused on ensuring the stability of the light sail during the launch phase. By employing innovative designs incorporating damping mechanisms and spring connections, they aim to mitigate the adverse effects of perturbations, ensuring a successful launch and trajectory alignment. The implications of Breakthrough Starshot's success are profound. Not only would it mark humanity's first foray into another solar system, but it would also unlock unprecedented opportunities to explore and study exoplanets, potentially uncovering clues to the existence of life beyond our own celestial abode. As the project marches forward, fueled by curiosity and innovation, the dream of interstellar exploration draws tantalizingly closer to realization. At its core lies the idea of deploying a mothership carrying thousands of miniature spacecraft, each no larger than a centimeter, to a high-altitude Earth orbit. Once in position, a synchronized array of ground-based lasers would focus their beams on the sails of these spacecraft, propelling them at remarkable speed within a mere 10 minutes. This acceleration, averaging at 100 kilometers per square second, is made possible by an illumination energy of approximately 1 terajoule delivered to each sail. The preliminary sail design suggests a surface area of 4 meters by 4 meters, with circular sails later proposed for optimal cost efficiency. The ultimate destination of these spacecraft is Proxima Centauri b, an Earth-sized exoplanet located within the habitable zone of the Alpha Centauri system. The goal is to position the fleet within 1 astronomical unit of this tantalizing world. From this vantage point, the craft's cameras can capture high-resolution images, potentially revealing surface features of Proxima Centauri b. Each spacecraft, aptly named Starship, is a diminutive vehicle weighing only a few grams. Propelled by a network of ground-based lasers with a combined output of up to 100 gigawatts, these star chips form a formidable swarm of approximately 1,000 units. This multitude serves a crucial purpose: to mitigate losses caused by collisions with interstellar dust encountered en route to the target. While these collisions pose engineering challenges, studies suggest that they may not be as severe as initially anticipated. Nonetheless, they may impact the quality of the sensors aboard the spacecraft. Breakthrough Starshot represents a paradigm shift in space exploration, but its ambitious goals come with formidable technical challenges. Light propulsion, the cornerstone of this initiative, demands enormous power. Even with a laser generating a gigawatt of power, akin to the output of a large nuclear plant, the resulting thrust is minuscule. To compensate, the spacecraft must be incredibly lightweight, with a mass measured in grams. This necessitates the miniaturization of essential components such as cameras, computers, communication lasers, and power sources, all of which must withstand extreme conditions of acceleration, cold, vacuum, and proton bombardment. Surviving collisions with space dust presents another hurdle. Each square centimeter of frontal cross-section is projected to encounter thousands of particles at high speeds, posing risks to the spacecraft's integrity. Furthermore, focusing a 100-gigawatt laser onto the solar sail faces challenges due to atmospheric turbulence, necessitating space-based laser infrastructure. Coherent combining optics of immense diameter are required to focus the laser light onto the sail, pushing the limits of current technology. At the heart of Breakthrough Starshot lies the Star Chip, a revolutionary nanocraft engineered for interstellar travel. These centimeter-sized vehicles, fitted with light sails, are designed to journey to Alpha Centauri, our nearest stellar neighbor, at speeds approaching 20% of the speed of light. Each Star Chip is equipped with a suite of miniature components, including cameras, processors, photon thrusters, and a power supply, all optimized for size and efficiency. The Star Chip's light sail, measuring no larger than 4x4 meters, is a marvel of engineering, potentially crafted from composite graphene-based material. Its thin yet durable design must reflect the laser beam while absorbing minimal energy to prevent vaporization. Additionally, the sail may double as a power source during the voyage, harnessing energy from collisions with interstellar atoms. Communicating with Earth poses its own challenges. A laser communicator, utilizing the light sail as a primary reflector, is envisioned to achieve data rates suitable for transmitting information across vast interstellar distances. While Breakthrough Starshot's flyby missions are designed for high-velocity passes of target stars, proposals for orbit insertion via photogravitational assist offer tantalizing possibilities for extended exploration. However, this maneuver requires sails even lighter and larger than those proposed for initial missions, underscoring the ongoing technological innovation necessary for interstellar travel. Claudius Gross, a German physicist, has proposed an intriguing extension of the Breakthrough Starshot initiative. Building upon the technology developed for high-speed interstellar travel, Gross envisions a second phase aimed at establishing a biosphere of unicellular microbes on otherwise transiently habitable exoplanets. In Gross's proposal, a Genesis probe would embark on a journey at lower speeds, traveling at approximately 4.6% the speed of light. This slower pace allows for a more deliberate approach, with the probe taking at least 90 years to reach Alpha Centauri A. Upon arrival, the sail would be configured to harness stellar pressure from Alpha Centauri A, redirecting the probe towards Alpha Centauri B, where it would arrive after just a few days. After this brief stopover, the sail would once again slow the probe, this time to a mere 0.4% the speed of light, before catapulting it towards Proxima Centauri. Despite the reduced velocity, the probe would still cover vast distances, arriving at Proxima Centauri approximately 140 years after its initial launch. To facilitate deceleration at this stage, Ross suggests employing a magnetic sail. This ambitious proposal opens up new possibilities for interstellar exploration and colonization. By leveraging the advancements made in high-speed space travel, we may one day be able to see distant exoplanets with life, paving the way for the expansion of life beyond Earth and the establishment of thriving biospheres in the far reaches of the cosmos.